Hello everyone, my name is Breno Orzari. I am a physics PhD student from Universidade Estadual Paulista in São Paulo, Brazil. And this work started as a research internship abroad in collaboration with some members of the Machine Learning for Particle Physics group from CERN, where we studied about sparse data generation for particle-based simulation of hadronic jets in the LHC. The LHC is a particle collider that allows for studies of the subatomic particles' interactions at its most fundamental level. An important piece of the events analysis is the comparison of the produced events with simulated ones, which nowadays are mainly generated using Monte Carlo-based generators. However, with the very large amount of data that needs to be simulated, this process can be very time and resources consuming. In PP collisions, the most common kind of produced particles are hadrons that are mainly found inside final state objects called hadronic jets that are sets of particles collimated in a given region of the particle detectors and account for a portion of the event simulation. The motivation for this work then is to speed up the simulation of hadronic jets using machine learning-based methods such as generative neural networks. Some important characteristics of a jet is that it is a very sparse object and it can be described by the properties of its constituent particles features. One thing to keep in mind here is that even though a list of the constituents might have an ordering in a given dataset, the jet's properties need to be invariant to permutations on the order of these objects. The dataset used throughout this work consists of high momentum jets originated from gluons. To deal with the sparsity of the data, each jet is represented as a list of the 100 highest momentum particle free momenta. The neural network model chosen is the variational autoencoder, given its capability of generating data through encoding the inputs into a low-dimensional representation. For the purpose of jet generation, we used application-specific reconstruction loss terms in the variational autoencoder loss function. The loss function is given by two terms, a reconstruction term and a KL divergence. The reconstruction error term was then divided into two contributions, ln and d, which is a permutation invariant term in the particle's properties that essentially measures the minimum distance between each input particle with every output particle and vice versa, and sums it over every input jet sample. And we also have Lj that is composed of two mean squared error terms in the input and output jets mass and pt that are weighted by gamma m and gamma pt, which essentially force the network to learn the jet's kinematics. Throughout the work, we used gamma pt equal to 1, and gamma m is distinct among the 4 models that we tested. 2 of them were trained using the early stopping technique with patients of 15 epochs with gamma m equal to 1 or 10. The other 2 were trained for 1500 epochs with gamma m also equal to 1 or 10. To evaluate the network generation capacity, we used the jet's mass, energy, pt, eta, and phi. As a quantitative measure, we used the sum of the Earth mover's distance, or Wasserstein distance, between each of the input and generated jet's features distributions. The model that showed the smallest EMD sum was the one trained for 1500 epochs with gamma m equal to 10. As it can be seen in the figures on the right, the distribution of the generated jet's features showed very good behavior, except for the generated jet mass on the top right corner. In conclusion, although the network couldn't generate jets with the correct mass distribution, other relevant quantities showed very good performance. The main issue so far then is the distinction between input and generated Jets mass distributions that might be caused by the network's lack of capacity to correctly encode the input data into the latent vector. A possible solution for this is left as a future step that would be to use the normalizing flows technique to learn a better posterior than the one obtained from Gaussian sampling. Thank you very much for your attention.